fast erosion. When you have finished to copy the sketch, then I give a couple of explanations to you, and then we are done. A couple of explanations. This is a cascade of linear reservoir. Who took hydrology among you may remember the Nash model. The Nash model is a cascade of linear reservoirs, and this is a Nash model with 3 reservoirs. And the number of 3 is adopted by the model, by IMOD. You may also increase the number, no problem. What's important is that the constant is the same for all of them, K fast. And you find the same sketch on my slides. What I don't remember if I use this symbol, Ks and Kf, so don't be concerned by symbols that are different. And another thing that I don't remember is whether I used 1 minus alpha for the slow or for the fast rather than alpha, but it doesn't change anything. What's important to note is the total number of parameters that I have introduced so far. And the parameters are Cmax, beta, alpha, Kf, Ks. 5 parameters. And now I stop with a final consideration before applying this tomorrow. You will see that the application is straightforward, but of course the theory is not as straightforward. I will try to put the video online soon, so if you want to get a look before tomorrow, it's possible. And a final consideration, you didn't see any water losses so far, but actually this model includes an evapotranspiration component. And I just want to anticipate, and I will explain you tomorrow very quickly. I want to anticipate not how it is computed, but how the model takes it into account. Basically, the model doesn't compute the evapotranspiration. You have to give to the model the evapotranspiration. You may remember that in the data that we used last time, there was a column describing evapotranspiration. You have to give it to the model. And we are not focusing in this course on computing evapotranspiration because they are empirical model. If one day you have the necessity to compute it, just refer to the web and you will see empirical formulations that allow you to compute evapotranspiration. What is important now to emphasize is how to take it into account into this model. So what is evapotranspiration? Basically, is a water loss that occurs at every time step at the expense of what? At the expense of the water stored in the catchment. If you have water stored in the catchment, you have evapotranspiration. If you don't have any water, you don't have evapotranspiration. So basically, this means that at the end of each time step, you have to update the value of W by subtracting evapotranspiration. This is what this model does. So again, at the end of each time step, you update the amount of the water stored in the catchment, of the water storage. Okay, we can stop here. And tomorrow I will give you the code, the R code, and we will try to understand